if a picture can speak 1,000 words, this would be the one I pick. All right. This shows us the history of the universe. All right. So here we are. Okay. Almost 14 billion years after the start of the universe. Okay. And as we understand it, the universe started from an infinitesimally small point and then expanded to give us space and time that we know today. Okay. Uh, so um, so we went through a period of very fast expansion in the early universe. Okay, so the gas was very hot at the beginning. Okay, that's why it's called the cosmic fireball. Okay, after a while the gas cooled. Okay, and we come to a period a few 100 million years after the start of the universe when the entire universe was just gas, actually mostly dark matter along with tiny bits amounts of gas. Okay, and out of this dark matter and gas, galaxies and stars formed. Okay, all right, and then galaxies grew to become, oops, the galaxies that we know today. Okay, so here's a spiral galaxy. Okay, this is a galaxy, the type of galaxy that we live in. All right, one with spiral arms. There are many other types of galaxies. So in the today, most galaxies, just over half of the bright galaxies in the sky are spiral galaxies. A bit less than half are these elliptical galaxies. So I'll talk about the details about these galaxies in a bit. All right, but most galaxies are much dimmer than either spiral elliptical galaxies. Okay, and they're lumped into another category that we call irregular galaxies because they don't have any particular structure. All right. Okay. Now, some of the big questions in astronomy. All right, and I'm going to address a couple of these in my talk. All right. Astronomers like to know when galaxies first form. All right. This is a nice picture. All right, but we don't really know exactly when galaxies form. Our best guess is a few 100 million years after the beginning of the universe, but it's still just a best guess at this stage. Um, we want to know how galaxies grow over time. Okay, so presumably galaxies start out being small with not many stars, and somehow they grew to become the kind of galaxies we see today. All right, so we're not interested just in how galaxies grow in size and in weight, in mass. All right, we also want to know why galaxies have the complicated structures that they have. Right? We know today that just about every massive galaxy, every heavy galaxy, has a supermassive black hole at the center. All right, and what we found also is that the mass of the supermassive black hole is related to the mass of the galaxy. Why that is, we don't understand. Okay, supermassive black hole is just occupies a tiny volume at the center of the galaxy. How does it know about the space around it? Right? We don't understand that. Okay, so what we like to know is when the supermassive black holes first form, and then how do they grow over time? Right. So I'm going to tell you about how we are finding supermassive black holes in young galaxies. And then finally, one of the big questions in all of physics, not just astronomy, okay, is what is the nature of dark matter? Okay, um, the gravity in the universe is dominated not by ordinary matter that we know about, hydrogen gas, for example, okay, but by a mysterious form of matter which exerts gravity, but which does not emit light, nor does it absorb light. Okay, I'm not going to be able to tell you today what dark matter is. If I could tell you, I'd be in Sweden collecting the Nobel Prize. Okay, but I'll tell you the ways astronomers are using to rule out certain classes of dark matter, or at least to test competing models for dark matter. All right, so I know that the audience here are not necessarily familiar with astronomy, so I'm going to start off with a very brief Astronomy 101 and then move on to more difficult topics. All right, so when we look at the skies, what do we see? We see stars in our galaxy, and we see stars in other galaxies. Okay, the universe is filled with galaxies. All right, with a lot of empty space between the stars and also a lot of empty space between the galaxies. All right. So each one of these bright objects you see here is an individual galaxy, and many of these small dots that you see here are also galaxies. They're not stars in our galaxies, but they're galaxies very far away. Okay. All right. So galaxies contain stars. Okay. Galaxies come in a variety of masses and sizes. Okay. Some galaxies contain only about 100 million stars. These are the irregular galaxies that I talked about. Okay, so 100 million, numbers in astronomy are very large. So I try to give you some way to relate to these numbers. Okay, so 100 million is about the population of the Philippines. Okay, and the big galaxies contain about 100 trillion stars. That's again a big number which is hard to relate to, but that is roughly 5 times the national debt of the US, which you might find quite scary, right? Okay, so galaxies are filled with gas as well as stars. Okay, but most of the gravity is produced by dark matter. Okay, all right. So this is a picture which would be familiar to people maybe over 100 million years ago before the invention of electricity. Okay, our cities are now so bright that we are completely disconnected from nature. Okay, so now this is a kind of thing you would see if you go to a dark area. In this particular case, in the southern hemisphere. This picture was taken from Argentina. Okay, so let me test you to see whether you recognize certain objects in this picture. All right, so what do you think this might be? Sorry? I'll come to that. Okay, so notice it's got this tail, right? So what does that remind you of? Okay, so let me ask Amruth since he's here. What is this, Amruth? A comet. Very good, thank you. I'm not going to ask you which comet it is, all right? This is the comet that appeared in 2007, about 10 years ago, all right? If you were in the southern hemisphere, you could have got a good look at this comet, all right? What about this thing here, right? This bright band across the sky. Milky Way, very good. Okay, so this is our galaxy. All right, when we look up at the heavens, we can see the galaxy we live in very well, in part because we are located towards the outskirts of the galaxy. Okay, all right, now what is this object here? A bit harder to guess. A nebula? Okay, so 100 years ago, that's exactly what we would call it. Okay, 100 years and more ago, when astronomers find diffuse objects in the sky, we call them nebulae. Okay, some of them have spiral arms, and they were called spiral nebulae. It's hard to imagine now, but less than 100 years ago, we did not realize that our galaxy is only one of many galaxies in the universe. Okay, we thought that our galaxy is the entire universe. So I'll tell you about the story of that a little bit later. Okay, now, Amruth, what is this galaxy? Thank you. So this is the Large Magellanic Cloud. Okay, so Magellanic because it's named after the Spanish explorer Magellan, who circumnavigated the Earth. Okay, so this is one of the 2 closest galaxies to our own Milky Way galaxy. All right. What about this thing here? What's the best guess? I'm going to keep asking Amruth until he gets drunk and can answer. So what is this one, Amruth? Small one. Okay, so this is the Small Magellanic Cloud, okay, also named after Magellan. All right, so when we look up at the skies, if you're in the southern hemisphere, the small and large Magellanic Clouds are very easy to see, okay? They actually look like wispy clouds in the sky. And when I first saw them, I thought they were clouds. Okay, until I realized that they were there every night and they did not seem to move very fast. Okay. All right. Okay, so here's a irregular galaxy. This is actually the Small Magellanic Cloud, this one here. All right. So irregular galaxies do not have any particular structure. These are the smallest and the dimmest of the galaxies. Okay. So this galaxy is about 1/10 the size of a galaxy. All right, now this is our own galaxy, the Milky Way. All right, So here, looking here is towards the center of the galaxy, right? And clearly the galaxy looks like a disk in the, well, it looks like there's a bright band. So it's clearly not a spherical ball of stars, okay? It's actually a flattened disk of stars, right? Now, this dark stuff that you see here, okay, this is actually small solid particles, which astronomers call dust. Okay, now dust has a very different meaning in everyday use. Okay, but astronomers use the phrase dust for small, small solid particles. How small? Oh, sorry. So here's again is the large Magellanic Cloud and the small Magellanic Cloud. Okay, how small? Typical dust grains in the interstar, in the gas between, in the space between stars, is about 0.1 micron. Okay, so that's much smaller than the size of the human hair. All right, to give you a sense of how small 0.1 micron is. Right, today we're worried about particles with sizes less than about 10 microns or so, or a couple of microns. Okay, P2.5, because those size particles can get into our lungs and maybe even dissolve into the bloodstream. So that's not very good. Okay, now this is an optical picture. Let me show you what happens when you take a picture in the infrared. Okay, so infrared is slightly longer wavelength than the optical. All right, so the amount of blockage by dust is dependent on wavelength. When we go into the infrared, we can now see all the way into the center of the galaxy. All right, and I'll tell you later on, this is the trick astronomers used to be able to measure the supermassive black hole at the center of our galaxy. Okay, there's still a slightly dark band here, but clearly it's not as dark as before. All right, now, okay, now here's the same picture here at the bottom. All right, this is just a sketch, an artist's conception of what our galaxy will look like if you're looking at it from the top. This is looking at it from the side, and we are over here, right? More towards the outskirts than towards the center of the galaxy. Now, the galaxy has, our galaxy, spiral galaxy, have very rich structures, okay? You can see that at the very center, looks like a spherical ball, okay? It's actually a spherical ball of gas, of stars, and astronomers call this the bulge of our galaxy. If our galaxy has a bar, this not the same kind of bar that you're sitting at, okay, is an elongated feature at the center of the galaxy. The flattened distribution of stars here is actually located, actually stars orbiting the galaxy in a disk. Okay, all right. And then if you look at other galaxies, apart from the bulge, apart from the disk, there's also this diffuse spherical ball of stars, which is the halo. All right. Now, how all these components assemble over time to look like what they do look today? That's one of the main questions astronomers are trying to address. Okay. All right. Now let me switch to another type of galaxy. Here again is the plane on the Milky Way. This is the Andromeda Galaxy. The Andromeda Galaxy is the closest spiral galaxy to our own galaxy. All right. So let me zoom it up. All right. But what I want to focus on is not the spiral galaxy itself. I want to focus on the small galaxies around this spiral galaxy. Okay, so let me put it across here. All right. So this small galaxy, if I zoom up, is a small elliptical galaxy. Okay, more or less a spherical ball of stars. Right. And here's another one. All right. So you can see that elliptical galaxies can be much smaller than spiral galaxies. On the other hand, elliptical galaxies can also be much bigger than spiral galaxies. Okay, so in this picture there are many galaxies in this picture. Okay, and all these yellowish ones are big elliptical galaxies. Right, and this one here is the biggest at the very center of the cluster. Is the biggest of them all. All right, so this galaxy would be many times the size of our own Milky Way galaxy. Okay, and many times more massive. Right. And once again, although this particular galaxy has no individual features, what we don't really understand is how these galaxies grew so much, okay, to attain their present-day masses as well as sizes. Okay, now although elliptical galaxies look like a ball of gas, okay, more generally they look like an American football. Okay, today we know that elliptical galaxies are really a ball having three unequal axes. Okay, so they're deformed in very funny ways. And depending on which direction you look at them, they can appear to be more or less circular, or they can appear to be elongated in ellipse. That's why they call elliptical galaxies. Okay, I'm going to be using this diagram a couple of times, so I'm going to spend about a minute on this diagram. So here what I'm plotting, okay, is the brightness of galaxies on this scale, okay. So brighter is towards your left, dimmer is towards your right, okay. And on this axis here, I'm plotting the number of galaxies you find per unit volume of space, okay, all right. So going up means you find more of this type of galaxies in a given volume of space. Now, S are the spiral galaxies that I showed you before. Okay, and you can see spiral galaxies are more numerous than elliptical galaxies. All right, towards the bright end of galaxies. But the most numerous galaxies are these small ones, the irregular and the dwarf ellipticals that I showed you. All right, they are much dimmer. Okay, they are on this side of the diagram. They're much dimmer, but they are much more numerous. So the universe prefers to form many small galaxies in preference to a few big galaxies. Okay, and I'll tell you later on, right at the very end of my talk, okay, that by probing the number of galaxies as a in this kind of diagram, we can actually rule out certain classes of dark matter and favor others. Okay, now the spread in brightness here, okay, is about a factor of 10,000. All right. So small galaxies are easy to see if they are nearby. Okay, but if they're far away, they're very faint. They're very difficult to see. In fact, they are impossible to detect, even with the big telescopes we have today. All right. So that gets me to the theme of my talk, where we use gravitational lensing, okay, to magnify background galaxies, to make them detectable with the big telescopes we have today. All right, so I'll come back to that in a bit. All right, okay, so as I said, right, one of the big questions is when did galaxies form and how did they grow over time, all right? So we're over here, all right, at the present day, okay? So nearby galaxies are big because they had time to grow. They're nearby, so they're very bright, okay? They're big and nearby, so they're bright. What we really want to know is galaxies over here. All right. So galaxies over here are small because they just started to form stars, and they're very far away. They're small, they're far away, they're very dim. Okay. So the key is how are we going to study these very faint, distant galaxies? All right. Let me give you a sense of the most distant galaxies we've found today. All right. So this diagram is reversed from previously. So this is the beginning of the universe over here, and at the present time we're over here. This is the Hubble Space Telescope. The data I'm going to show you today is from the HST. All right, and these are the two most distant galaxies that we detected today. All right, so this galaxy is seen just about 600 million years, 500 to 600 million years since after the beginning of the universe. Right, this one is maybe 700 or 800 million years. Okay, but the thing is, that's just one of them here and one of them here. All right, we are just barely able to detect the most bright, most distant galaxies. Right. The question is how are we going to find more of them, okay, and be able to study them. All right. Okay, so this galaxy here, if you're wondering what it looks like, this is what it looks like. All right. So this is the region of sky in which it resides. Okay. So you can see many, many galaxies in this picture. Virtually every dot in this picture is a galaxy. Some are relatively close, and then some are much further away. This particular galaxy, you can't even see in this, you probably can't even see from the back, okay? But if you zoom it up, this is what it looks like, right? Just a little blob with some weird features, right? What we like to do is to make this galaxy look bigger, all right? So we can study features in this galaxy. So that's where gravitational lensing will come in. All right, okay. Now, how can we study galaxies which are younger? Okay, well, the key is that when we look out into space, we are also looking back in time. Right? the universe is a natural time machine. All right? We want to look back in time. All we need to do is look as far back as we can into space. All right? So let me describe that, explain that in a bit more detail. All right. Okay, let's consider the time it takes for light to travel between the Earth and different objects in the solar system. Okay, so the time it takes light to travel from the Earth or from the Sun to the Earth is about 8 minutes. Okay, so when we look at the Sun, the Sun does not look as it appears now, but as it appears 8 minutes ago. If the Sun was to turn off its light, we would not know for another 8 minutes. Distance between the Earth and Mercury is about 5 minutes. So if we ever send a man to Mercury, and we want to talk with that person, all right, it'll be a very slow conversation. We'd say something, it takes 5 minutes for the message to get to him. He replies, takes 5 more minutes to get back. All right. Venus is about Venus is closer to the Earth, so it only takes 2 minutes. The Moon, of course, is very close, only takes a second or so. Right. For those of you who've seen pictures of the videos of the Apollo mission to the moon, right? You would have noticed that the astronauts take a little bit of time to reply, okay? And that's because of this lack of 1 second for radio communications get to the moon and then back from the moon again. For Mars, it's about it takes about 4 minutes, okay, for light to travel between the Earth and Mars. For Jupiter, it's 40 minutes. Saturn is now 1 hour. Uranus, 2.5 hours. Neptune, 4 hours. Pluto is about nearly 5 hours. Okay, so if we want to communicate with Pluto, right, all we can do is send a message, wait for 5 hours for the message to get there, and then wait another 5 hours for the message to get back. All right, all we could talk about, the conversation we would have is just a couple of exchanges a day. All right, so when we look at Pluto, we see how Pluto was 5 hours ago. All right, now that doesn't seem like a big deal until you look at stars and galaxies. Okay, Alpha Centauri, that's the closest star to the sun, to the Earth. Okay, and it takes like 4 years to travel between the Earth and Alpha Centauri. Okay, so if you want to communicate with Alpha Centauri, we send a message today, and we might get something back in about 9 years' time. This is our galaxy. Our galaxy is about 100,000 light years across, okay? Which means it takes light 100,000 years to get from one end to the other. All right. So when we look at the stars over here, okay, we're seeing these stars as they were 100,000 years ago. If you look at the Andromeda Galaxy, we see the Andromeda Galaxy as it was 2.5 million years ago. Right? Now, 2.5 million years sounds like a very long time, but the age of the universe is about 14 billion years, so that's still very small. Okay? Andromeda is very close to us. Right? Now, 2.5 million years ago, right, the first humans had not left Africa yet. Right? All right, now here's a rendering of the galaxies which are close to us. So this is our galaxy. The large and small Magellanic Clouds are over here. This is the Andromeda Galaxy. Okay, so our galaxy is part of a group of a few tens of galaxies which are traveling together through space. Okay, bound to each other by gravity. All right. There are many more galaxies. Okay, so on this scale, the picture I showed you before would just lie in this small circle here. All right, and this scale here is now 5 million years. Okay, the travel time is 5 million light years. Okay, so for example, this galaxy here is located at a few tens of millions of light years from us. It takes tens of millions of years for light to travel from that galaxy to us, and that galaxy looks like this. Okay, so it's about 50. So we see this galaxy as it was 15 million years ago. Right now, that's still very small. Okay, remember when we look back at this galaxy, we are seeing these galaxies as they were about 13 billion years ago. All right, so we look very deep into space. We look way back into time, all right, to the epoch when hopefully galaxies were just beginning to form. All right, so that's how astronomers study young galaxies. Okay, we use big telescopes, look for very faint galaxies very far away. Okay. All right. Okay, so let me show you a few pictures of very faint galaxies. Okay, um, very young galaxies. Okay, so this particular picture was taken by the Hubble Space Telescope. Okay, it's called the Extreme Deep Field. Okay, here's the size of the moon in the sky. The picture I'm going to show you is this big. Okay, so it's just a tiny patch of the sky. All right, and the Hubble Space Telescope stared at this patch of the sky for 23 days. Okay, now 23 days is a long time to look at any single area of the sky. All right, a typical observing program with the Hubble Space Telescope is a few hours. All right, 23 days is a very long time, and it was only possible because the director of the telescope decided to use his discretionary time to do this program. Okay, so here are a few galaxies which are seen a few 100 million years since the beginning of the universe. Right. So let me show you this one here first. Right. So this galaxy is seen just about 600 million years since the beginning of the universe. All right. It's this blob here. All right. Now I'm showing you this because the galaxy is far away. Okay. Beginning to form stars. They're not just dim, but they're very small. Okay, even with the most powerful telescope, the Hubble Space Telescope, all we see is a blob. Okay, I'll show you more blobs. Here's another one. Okay, 600 million years since the beginning of the universe. Another blob. Here's another one. Okay, now just 500 million years before the beginning of the universe. Okay. And here's another one, just 400 million years since the beginning of the universe. Right? So galaxies far away are basically too small for us to see any features. Okay, we need help. All right, and that's where gravitational lensing comes in. Okay, so here are the 4 galaxies far away again. Okay. Oh, by the way, I welcome questions as I go along. All right. I realize all this is brand new to you. Okay, so if you have questions, just shout out. All right. Okay. Now, so I told you, as we look very deep into space, we also look back into time, right? But the question is, how do we know how far back we're looking back in time? In other words, how do we know the distances to these galaxies, right? Where do all these numbers come from? Okay. All right. So to understand that, I have to go back about 100 years to the time of Edwin Hubble, after which the Hubble Space Telescope was named. Okay. Now at the time, as I said, astronomers, physicists, scientists, okay, did not know that about the existence of other galaxies. Okay. When we look up the sky, we see objects which have spiral arms. The Andromeda Galaxy being a very good example. Okay. The big question 100 years ago is, what are these spiral nebulae? Okay. All right. Now this question was solved by Hubble. Okay. And Hubble's contribution was in measuring the distances to these galaxies. Okay. Now I don't have time to tell you how he did it. All right. He used a kind of a type of star called a Cepheid variable, which varies in brightness with time. Okay. The period of the brightness variation is related to how bright these stars are. Okay. So when we look at galaxies, we can see other Cepheid variables. All we have to do is measure how long they change in brightness. Okay. We can measure what the brightness appears to be. We know what their true brightness should be, so we can tell the distance. Okay. All right. Now each one of this dot here is a spiral nebula. The distance to a spiral nebula measured by Hubble. Okay. So distance increases this way. On this scale, the size of a galaxy is just a dot at the origin here, 0, 0. Okay. So that tells us that Hubble told us, the rest of us immediately, that this so-called spiral nebulae in the sky today, what we know today to be spiral galaxies, are actually individual galaxies, individual worlds of their own. Okay. Now, what Hubble also discovered is this. Here I plot the speeds of the galaxy. Okay, positive here meaning the galaxies are moving away from us. All right, and what you can see, okay, is that generally speaking, the further the galaxy, the faster it's moving away. Right, so nearby galaxies are not moving away at very high speeds, but distant galaxies are moving away at very high speeds. Okay, all right, so I'll tell you that in a second. All right, so this line here, okay, is just the best fit to the data points. All right, the slope of this line here is what is known today as Hubble's constant. For those of you who heard about Hubble's constant, okay, Hubble's constant tells us how fast the galaxy is moving away from us for a certain distance. Okay, so why does this tell us the universe is expanding? All right. All right, so I'm going to represent the universe on a two-dimensional space, okay, something you might be familiar with, right? Imagine I have a balloon, okay, and I paint dots on the surface of the balloon, each dot representing a galaxy, okay? Then I blow up the balloon, so the balloon expands, and the distance between galaxies also increases, all right? So that's to represent the expansion of the universe. All right, so here's my dots on my balloon, okay? I wait some time, okay, for the balloon to expand by a factor of 2, twice as big as it was before. All right. Now, let's imagine that this is our galaxy, and this is the nearest galaxy to us. Okay. Let's say that initially the two galaxies are separated by a distance of 1 in certain units. This is centimeters. 1. Okay. We wait for the universe to expand by a factor of 2. So naturally, this galaxy now be 2 units away. This galaxy here is 2 units away. We wait for the universe to expand by a factor of 2. This galaxy is now 4 units away. All right. So you can see that over this time interval, this galaxy has moved at a speed of 2 units in that time, or rather 1 unit, 2 minus 1, 1 unit in that time. This galaxy has moved at 2 units in that time. Right. If the galaxy is twice as far away, it moves at twice the speed. 4 times away, 4 times the speed. Okay, so that's why this diagram here tells us the universe is expanding, okay, and expanding at a constant rate. Okay, if you're wondering how long it will take the space, the distance between you and I, all of space is expanding. If you're wondering how long it will take for the distance between you and me to expand by a factor of 2, well, the answer is about 10 billion years. Okay, so that's much longer than the time we have in this place tonight. Okay, it gives you a sense of how quickly the space is expanding. All right. Okay, here's a modern diagram. So Hubble's diagram is nearly Hubble's original diagram. This one, okay, was taken in the 1920s. Here we are close to 2020. Okay, and each one of these points here is an individual galaxy. Here I plot its distance, okay? Here I plot its speed, all right? Today we can only measure, oh, and by the way, Hubble's diagram, original diagram, would occupy just this tiny volume of space here, right? So you can see how much further we probed, we've been able to measure the distance of galaxies, okay? Now what you notice is that as you go to larger distances, the number of galaxies fall off. Okay, that's not because we cannot detect galaxies in this small, relatively small distance here as I'm talking about. All right, it's just because measuring the distance of galaxies, we need to find this special kind of star called Cepheid variables. Okay, if these galaxies are too far away, we just cannot detect these stars anymore. Okay, we can just detect the stars collectively, but not individual. We cannot separate out individual stars. All right. Now, the actual size of the universe is about 10 times bigger than what I show here. All right, so this is just a local part of the universe. Now, what astronomers do to infer distances these days is that we don't actually measure distances. We just measure the speeds of galaxy moving away from us. Okay, what we call the recession velocity. Okay, because if we can measure the speed, all we need to do is go across here to this line, and then go down, and that tells us where the distance is. Okay, so the key to measuring distances to galaxies is actually measuring the speeds of galaxies moving away from us, what we call the recession velocity. Okay, the next question then is, well, how do we do that? How do you measure the speeds of galaxies? Well, we use an effect which is familiar to you. Okay, it's called the Doppler effect. So the car is moving towards you and then away from you, okay? And as it moves towards you and then passes you, its pitch changes, okay? That's called the Doppler effect, okay? That's something I noticed when I was a kid, riding in my dad's car. And I thought I was a little bit crazy, okay? I thought there was something wrong with my hearing. I never dared to ask my dad what was going on, okay? It wasn't until I got to university that I learned about the Doppler effect, and that was perfectly normal. Well, reasonably normal. Okay, and astronomers use the same effect to measure the speeds of galaxies. Okay, so the reason why there's a Doppler effect is that sound waves are compressed in the direction of motion, so the pitch is higher. Okay, and the wavelength of sound waves is stretched opposite the direction of motion, so the pitch is lower. Okay, so the horn sounds at a higher pitch when it's coming towards you, and then a lower pitch when the car moves away from you. Right, that's the Doppler effect for sound. That's an equivalence for light, okay, because light also propagates as waves. All right. Okay, so let me show you schematically how astronomers measure speeds. Okay, this blue line here, okay, is the intensity of light from a galaxy as a function of wavelength. Okay, and this is the optical part of the spectrum. All right, and this kind of galaxy is a star-forming galaxy. It's a spiral galaxy. Okay, if you look at a spiral galaxy, you find that it produces more light in the blue than in the red part of the spectrum. Okay, and that's because spiral galaxies are forming stars. Okay, young hot stars tend to emit most of the light in the blue. Okay, all right. So this is what the spectrum of a galaxy would look like. Now this is a spectrum of a nearby galaxy. Okay. Now if the galaxy is moving away from us, okay, the light wavelengths will be shifted to longer wavelengths in the same way that sound waves are shifted to longer wavelengths when the car is moving away from us to a lower pitch. Okay, so the entire spectrum is shifted towards longer wavelengths. All right. Now, if the galaxy is moving away from us at half the speed of light, okay, the spectrum in the blue will be shifted all the way to the red. Okay, all right. And galaxies at the edge of the universe, a few 100 million years after the Big Bang, are moving away from us close to the speed of light. Okay, that's how fast the universe is expanding over time. All right, so now all astronomers need to do to then measure the distance of galaxies by measuring its speed is we do this. We observe the light, okay, over individual narrow bands. Okay, we use what we call a filter. Right, we just restrict the wavelength ranges. Or in other words, we just look at the color of a galaxy by using different filters. Okay, same as a camera filter, right? You can put a red filter on a camera or a blue filter. All right. So a nearby galaxy, okay, will appear to be very bright in the blue, okay, and dimmer as you get towards the redder part of the spectrum. Now, if you go to this green line here, a more distant galaxy, well, this galaxy would be very dim in the blue, okay, bright in the yellow, and then less bright in the red. If you look at this galaxy, which is even further away, it appears to be very dim in the blue and yellow, and only pop up in the red. Okay, and this is the most common way astronomers use today to measure the speeds of galaxies. All right, so here's a real picture showing 4 different galaxies. So each one of this row is an individual galaxy. All right, and each one of this column here is a different filter. Right, so this is the yellow part of the spectrum. This is the red part of the spectrum, and then this actually goes into the infrared part of the spectrum. Okay, so wavelength increases this way. All right. Now this circle is to draw your attention to where a distant galaxy is. For example, this galaxy here, you don't see it in the optical. You don't see it in the yellow part of the spectrum. You don't even see it in the red part of the spectrum. You only see it in the infrared part of the spectrum. Okay, that tells us immediately that this galaxy must be very far away. Okay, so from the Doppler effect, we can infer how fast it's moving away from us. Okay, from the Hubble constant, we can infer how far the galaxy is away. All right, how far it is away, we can tell how long light has taken to travel to us. Okay, and therefore how old the galaxy must be. All right, so all these 4 galaxies here are seen about 800 million years after the Big Bang. Okay, so they're close to the age of the universe. Right? All right. Okay, so the key is that beyond nearby galaxies, we don't actually measure distances. We measure recession velocities, and from that infer distances. Okay, um, here's a very important plot in astronomy. Okay, um, again, what I'm plotting here is the brightness of galaxies. Again, brighter to your left, dimmer to your right. The vertical scale here is the number of galaxies per unit volume of space. Okay, so going up means you find more galaxies in a given volume of space. Right? And as you can see, bright galaxies are not very common. Right? As you go to fainter galaxies, they become more common. Right? That's I'll show you why that is a bit later on. Okay, but that's how the universe formed. So related to how galaxies actually form. Right? Okay. Now the key here is that at this age, okay, which is about 650 million years after the Big Bang, even with our almost powerful telescopes, all right, the difference in brightness that we can see between the brightest and faintest galaxies is only about a factor of 100. Okay, recall that in nearby galaxies, right, the difference between the dimmest and brightest factor of 10,000. Okay, so the reason why we don't see any dots here, there's no data here, it's not because there are no galaxies here. They're basically too faint to detect. All right, and I'm going to tell you towards the end of my talk, it is this crucial area here, the number of galaxies towards the fainter end of the population, that is the key to differentiating between different models for dark matter. All right, so I'll come back to that in a little bit. Okay, now of course, for these very distant galaxies, we also like to study the appearances. But as I showed you, all these galaxies looks like just a blob. Okay, so how are we going to study the structure of these galaxies very far away? Well, the key is to use gravitational lensing. Okay, so gravitational lensing is a gift from Albert Einstein. All right, and this is one of the quotes of Einstein in trying to explain his work to his son. Okay, on his son asking, "Why are you so famous?" Right? Einstein replied, "Well, you know, when a blind beetle crawls, if you're blind and you walk over the surface of a globe, you do not realize that the globe is not flat. Okay, it's curved. All right. He noticed that the globe is curved. All right. By that he means that space-time is warped. All right. Okay. So you've probably seen this kind of exhibit in museums. All right. So if you take a rubber sheet, okay, and you draw a regular grid on it, okay. So this regular grid is to represent the distance between 2 points in space. Okay. Now, if the universe did not have any matter, all right, the space between the space on this grid would be the same no matter where you are, right? But if you put a massive object like the sun, or a star, or a galaxy, okay, massive objects warps space-time. Okay, so if you put a ball on this rubber sheet, of course the rubber sheet is going to sink. Okay, now the dimensions of space, okay, changes around this rubber ball. Okay, that's what we mean by warped space. Okay, not just space is warped, but actually time is also warped. Okay, time runs differently as you get close to a massive object. All right, so space-time is warped. Now, what happens if you warp space-time? Okay, is that light no longer travels in a straight line. So ordinarily, light would. Oh, sorry. So we are over here. So here's a star. So ordinarily, if the sun was not here, light would just travel in a straight line. Okay, but because space-time near the sun is warped, okay, light curves around the sun. Okay, the amount of curvature is incredibly small, but it was measured about less than 100 years ago. Okay, actually about 100 years ago. Okay, the amount of bending is 0.9 arc seconds. Now that may not mean very much to you. Okay, but the displacement between the actual position of the star in the sky and the position we measure it, because the light is warped by the sun, is about 1/2000th time the diameter of the moon. Okay, and this was verified in expeditions to look to take pictures of stars around the sun during the eclipse of the sun, okay, by the moon. All right, and it was found then that indeed stars near the limb of the sun appeared at a slightly different position than what they would where they appeared when the sun was not there. All right, and this verified one of the predictions of Einstein's theory of general relativity. Okay, now the degree to which light is bent depends on the mass of the object. Okay, the sun is not particularly massive. Galaxies are much more massive. Okay, I'm going to talk about galaxy clusters, which are even more massive still. So the amount of bending can be a lot. Okay, all right. Now let me show you how we take advantage of gravitational lensing. Okay, and what it does. Imagine that we're over here, the Earth. Imagine that there's a source over here, a star or a galaxy. Okay, so we're going to be talking about galaxies, so imagine that this is a distant galaxy. Now, ordinarily, light from the galaxy that travels to the Earth would get to the Earth. Light which is not directed to the Earth would pass by the Earth. We will not intercept this light ray or this light ray. Okay. Now, if you put a massive object between Earth and the background galaxy, what happens now is this. Light that travels directly to the Earth will still get there. Light which would ordinarily be directed away from the Earth is bent, okay, so that it gets to the Earth. All right. Another light ray here is also bent and gets to the Earth. Now, we think that light travels in a straight line. So obviously, I see this gentleman here. I think it's over here and not over there. Right? We think light travels in a straight line. The consequence is we see multiple images of the same source. So not only do we think that there's a galaxy over here, we see the same galaxy in this direction, okay, due to the bending of this light ray, and we see a galaxy in this direction due to the bending of this light ray. Okay, so this effect is called gravitational lensing. The result is that it produces multiple images of the same source. Okay. Now, reality is a bit more complicated because I'm just plotting space in 2 dimensions here. Right? Space is actually 3 dimensions. A light ray which comes out of the board slightly will also be bent by this massive object to get to the Earth. Okay? The result is, if you have a perfect alignment, you see a ring. Here's the Earth, here's the background object, and here's an intervening massive galaxy, which is a massive object, which is another galaxy. All right? If all 3 are perfectly aligned, okay, if this object is a perfect spherical distribution of stars, we would see a complete ring in the sky. Okay, and we see many examples of this. So here's a real picture. All right, this object here is this object here. This is the galaxy between us and the background galaxy, which is now being lensed into a near complete ring. Okay, it's not perfect. It's not a complete in part because the alignment is not exactly perfect. Okay, in part because this galaxy is not entirely a spherical ball of stars. It's got some shape. Okay, but it's pretty darn close to being a ring. Okay, so in honor of Einstein, we call this an Einstein ring. All right. Okay. All right. Now the position of the lens object in the sky, as well as the appearance of the lens object in the sky, depends on these things here. All right. I'm going to go through this in some detail because later on I'm going to tell you how we use lens images to infer the mass distribution of the lensing object. Okay. All right. So first of all, it depends on the alignment. Okay. So you've seen that if we have perfect alignment, we get and if the intervening object is a spherical mass distribution, we get a ring. If the alignment is not perfect, as in this case, right? Here's the massive object. Okay. It's not perfectly aligned. All right. We don't see a ring. Okay. We may see multiple objects in the sky. Okay. Or we may see multiple arc-like images, which I'll show you in a minute. Okay. All right. So in generally, what we see in the sky depends on the alignment. It depends on the shape of the lensing object. It depends on the distance to the lensing object. What we see for the lens image also depends on the actual appearance, the true appearance of the background galaxy, okay, as well as the distance to the background galaxy. Okay, so what we see depends on all these things. All right. All right, so to give you some sense, I'm going to show you some animations that one of my graduate students did. Okay, and what you see here is this green dot here is the object that's doing the lensing, so it's this object here. All right, a red dot will appear soon. Okay, right now you don't see the red dot because it's exactly behind the green dot. All right, now if this lensing object is a spherical distribution of stars, like a ball of stars, then you would see a ring, an Einstein ring. Okay, now I'm going to show you what happens when the alignment becomes not so good. So the red dot is the background object. So as alignment becomes less perfect, you first start off seeing a small arc on one side and a big arc on one side and a small arc on the other side. Okay, so that's what you see. All right. If the if the lensing object is not a perfect sphere, but it's an elliptical distribution of stars, so it's like an American football, if you like, which is what the typical elliptical galaxy is. All right, we see these 4 blobs. Right. So once again, here they are perfect alignment, and then as you get poor alignment, you see big arc on one side and a small arc on the other side. Okay. So the appearance of the lens depends on these factors that I mentioned. Okay, so I'll show you some, okay, so here again, all right, so in this case, this is an elliptical galaxy, perfect alignment you see 4 images of the same galaxy. Less perfect alignment, it's, these 3 images are off to one side, okay? And we see these things in the sky quite frequently, all right? Here is the lensing object, okay? And here is the background lens galaxy, 4 dots, okay? In this case, 4 dots here. This 5th dot here, that's just the center of the lensing galaxy, the intervening galaxy. Okay. In honor of Einstein, we call this an Einstein cross. Okay. All right. So here's an example where the alignment is less perfect, and we have an elliptical lensing object, right? Big arc on one side and a small arc on the other side. Okay, and here's the intervening galaxy, right? You can see it's not a perfect circle. Looks like an elongated galaxy. Yeah.
How can you tell this is actually the same object?
Oh, very good question. Okay, very good question. Okay, so what we actually do is we take a spectrum, or we measure the colors of this object and this object. It's no coincidence that both look the same color. Okay, because the same object has to have the same color or the same spectrum. Okay, so to be sure, we have to take a spectrum. Okay, that's a very good question. All right, now our work, we don't just use an individual lensing galaxy, we use a cluster of galaxy. Okay, so a cluster contains many galaxies, up to about 1,000 galaxies. Okay, they all move through space together because they're bound together by gravity. All right, and galaxy clusters are the most massive objects in the universe, so they produce the most bending of light. Okay, so they're the most powerful gravitational lenses in the universe. All right, this is what a galaxy cluster produces. Okay, we see many arcs. Okay, and you can see that different arcs are different color. Okay, so these are different galaxies behind the cluster being lensed by the cluster. Okay, all right. Now, what gravitational lensing does? Okay, it magnifies the object in size. Okay, you can see these arcs are really big. Okay, so we can study the appearance. Okay, when it would otherwise not be possible. Without this intervening cluster, right, this galaxy will appear just like a little dot in the sky. Right? The second thing is that lensing magnifies the brightness of the galaxy. So we can now detect galaxies which would otherwise be too dim to be seen, even with our most powerful telescope. The big problem with lensing is that the images are all distorted. Clearly, galaxies don't look like lines in the sky. Okay, and it's because clusters have very complicated mass distribution. Okay, so that the resultant images are highly distorted. Okay, by distorted, of course, I mean the observed appearance is not really the true appearance. Right. So the key is we need to correct for this distortion. All right. In other words, we need to derive the mass distribution of this cluster of galaxies. Now, that would be easy if the mass is produced by each individual galaxy. But we know today that the bulk of the mass in clusters is not in these galaxies. Okay, it is this stuff between galaxies, which is dark matter. We don't really know what it is. Okay, it does not emit any light, but it produces most of the gravity. All right. So we need to derive the mass distribution, the lensing power of the cluster, to know what the galaxy actually looks like, and also how bright it is. Okay, and how bright it is key to allowing us to determine whether these are really faint galaxies or bright galaxies. Okay, now to infer the mass distribution, we just invert the problem. Remember, if you know what the shape of the lens is, remember that the appearance of lens galaxies depends on the shape of the lenses. Conversely, if we know what the positions, okay, and the appearances and the distances of the lens images, we can then invert the problem to figure out the mass distribution of the clusters. Okay, so that's what we do. All right, I'm not going to show you how we do this in practice. I'm just going to show you some results. Okay, so this is work from one of my previous graduate students. Okay, this yellow things here, this is a galaxy cluster. Okay, a very massive galaxy cluster. This object here is actually located far behind the cluster, and it's been magnified by a factor of 6.3. Okay, it looks reddish in the middle and blue out here. Okay, I'll show you later. These are actually spiral arms in a distant galaxy. Okay, the magnification here is 6.3. 6.3 times brighter than what it otherwise would be, and more importantly, 6.3 times bigger. So imagine it was 6.3 times smaller. It'd be much harder to see features. Okay, and this galaxy is lensed multiple times. So here's the same galaxy here again. You can see probably the same galaxy, right? In red in the middle, blue out here. This is just a galaxy which is part of the cluster itself. And you see it again here, right? It's lensed 3 times. Okay, so there are many other lens images towards this cluster, and that allows us to determine the mass distribution of the cluster. All right. So here are the same 3 images I showed you before. Okay, and after we correct for the distortion due to the lens, this is what the galaxy looks like. Okay, obviously it looks the same for each one of these lens images because it's the same galaxy. So that's how we infer the mass distribution of the cluster and correct for both the size and brightness of the lens image. One of the things astronomers are interested in, okay, is how supermassive black holes grow over time. All right. Here's a picture towards the center of our own galaxy, in which lurks a supermassive black hole with a mass of 1 million suns. Okay, so I'm going to focus on this tiny patch of sky here. Right? I'm going to zoom it up, and then if you could press the button, each one of these dots is an individual star. Okay, and we can measure how the stars are moving around the center of a galaxy. This cross here is special because you will see in a little bit that the stars seem to be orbiting around this position. Okay, and at that position we see nothing, no light. Okay, from the motion of stars, we can figure out what the mass of this object is. Okay, and we figure it's about 1 million solar masses, but even with the deepest images, we cannot see any light from it. Now, this kind of measurements of mass to supermassive black holes, we can only do in nearby galaxies. Okay, and the reason is because we either need to measure the motion of individual stars, which really is only possible in our galaxy, or what we're left with is to measure the motion of gas or stars as a collective whole, not individually, but as a collective whole, okay, around the center of nearby galaxies. Okay, so this is a disk of gas around the center of a nearby elliptical galaxy. Okay, and from the motion of the gas orbiting this center, we can figure out what the mass of the supermassive black hole is. In exactly the same way as we figure out the mass of the sun. You know, how do we know what the mass of the sun is? It's by measuring the orbits of planets around the sun. Okay. All right. I'm going to show you a work that my student is doing, or has done, all right, to infer the mass of the supermassive black hole in the biggest, most massive galaxy in this particular cluster with this telephone number. Okay, so here's the same background galaxy, which is lensed 4 times. You see 4 images of the same galaxy. All right. Now there are many more lens images, and from these lens images, we've reconstructed the mass distribution of the cluster. Okay. All right. So I'm not going to zoom in into this patch here. All right. Okay. So here's the same patch. This yellow dot here is this big galaxy here. This little dot here is this galaxy here. So the galaxy is in the cluster. All right. And this blue stuff here, that's the lens image of a background galaxy. This picture is a combined multicolor picture, right? Red, yellow, and blue. Now just look at the blue part of the picture. In blue, these galaxies don't appear because they are relatively red, okay? And each one of these features here, this is an individual feature in a spiral arm of a background lens galaxy, okay? All right, now I'm going to show you what happens when we look at the data very carefully. Oh, by the way, the cross here is just the center of this galaxy. All right, I'm going to focus on this feature here, which we call L1. All right, let me direct your attention to this panel. This side, which is colored blue, this is the actual image of the lens galaxy. And this side, which is colored gray, is our model predictions for what these features here will look like on this side, okay? Because these features are just reflection of itself across this part of the image due to lensing. Remember, lensing produces multiple images. Okay, so this part here is just the counterpart of this part, right? This feature here is a counterpart of this feature. This feature here just a counterpart of this feature. All right. Now, in this model, we've not put in a supermassive black hole in this galaxy. Okay, and our model then predicts this feature to be straight. Okay, which is different to its curved appearance. All right. Now we put a black hole at the center of the galaxy. Here's the actual data, and here's the model predictions. Okay. Now this feature is much longer. Okay, but it does not curve like this feature here. Now we put a black hole over here. Again, this is actual data. Put a black hole over here, and then we predict what the other side should look like. Now we can see this feature to be curved. All right. Okay. Now in this last panel here, we also put a black hole at the center. Okay. Black hole at the center doesn't do very much because it is a black hole over here that is actually causing the curvature of this particular lens image. All right. So what we have here is an offset, a supermassive black hole which is offset from the center. Okay. And actually that's becoming more common these days. The way we think supermassive black holes grow in mass, okay, is to merge with each other. Okay, all right, so let me just quickly go through how we test dark matter, all right? This is the big daddy in astronomy. Okay, we don't know what dark matter is. All we know is dark matter exerts gravity, okay? But it does not absorb or emit light, so we cannot see it, we cannot probe it. The only way we know it's there is due to its gravity, all right? There are many different models proposed for what dark matter is. Okay, I don't have time to describe them in detail. All right, the most popular one today is dark matter comprises some kind of cold, massive particles. By massive, I mean particles which are much more massive than the hydrogen atom. Okay, hundreds of thousands of times, maybe millions of times more massive than the hydrogen atom. Okay, all right. And cold because it's not moving very fast. It's quite a massive particle. Here's another kind of dark matter which was proposed, which has been investigated for the last couple of decades. But it's only in the last few years that we can actually predict what kind of galaxies this kind of dark matter would form. All right, it's called wave dark matter. All right, so I will not talk about that in detail. I'm going to talk about how we believe galaxies form. All right. So the bulk of matter in the universe is dark matter. All right. Now you can think of dark matter as individual particles with some mass, which we do not know. All right. Imagine that these dark matter particles are uniformly distributed through space. Okay. If that was the case, all right, if the distance between each dark matter particle was exactly identical, we wouldn't be around today. Okay, because galaxies and stars will not form. Instead, we need some small degree of inhomogeneity, some non-uniform distribution, okay? And we can see that imprinted in the cosmic microwave background, for those who are familiar with that, okay? Doesn't matter. We know from studies of the early universe that matter in the early universe was slightly clumpy, okay? When I say slightly, I mean very slightly, okay? But this slight clumpiness led to us, all right? So here, these particles here are closer together than these particles over here, right? Now these particles feel each other through their gravity. They're attracting each other by gravity. So over time, the particles are going to collect together where the density of these particles are higher than average, okay? And as time goes on, more and more particles will be attracted into this. So as the mass of this collection of particles grow, their gravity becomes stronger, they attract even more particles to them, okay? And that's how galaxies are, we think, form from dark matter. So I'm going to show you a computer simulation of how dark matter form galaxies, okay? So so the redness here, there are millions of dark matter particles in this simulation, okay? And I start from just after the beginning of the universe till today. So we're very close now to the present day universe, okay? So each one of this dot, which you can't see from the back, okay, is an individual galaxy, all right? So this tiny inhomogeneous today with gravity, okay, form the galaxies we see today. Now, the key here is that these simulations here that I showed you before were done with cold dark matter, all right? Now, here's a plot of the brightness of galaxy versus the space density of galaxy, number of galaxies per unit volume. In the cold dark matter, this is how we predict the number of galaxies should depend on their brightness. Okay, the universe prefers to form many more low mass galaxies than high mass galaxies because we need time for the dark matter particles to come together. Big galaxies, dark matter particles take longer time to come together. That's why there are fewer of them. Now, with wave dark matter, this is what we predict. Okay, in the wave dark matter model, the number of small galaxies, this plot here actually turns down at small galaxies. Okay, wave dark matter suppresses the formation of small galaxies. All right. Okay. So so the key is to probe. So this yellow dotted line here. Okay, this is about how far we can probe with very deep images of the sky without the benefit of lensing. Okay, so without lensing, we cannot tell the difference between these curves. They all predict much more or less the same number density of galaxies in space. Okay, but if we could probe a little bit deeper, then we would see these lines being different. Okay, the space density of galaxies being different. So the key is to go just a little bit deeper than what we can today without lensing, even with the most powerful telescopes. Okay, so I'm really running out of time. Let me just show you the results. Okay, all right. Now I don't have time to talk about this in detail. This is the amount of magnification by the galaxy cluster. This factor 10, factor 100 magnification. This again is a space density of galaxies. This is what cold dark matter predicts. These lines here, these 3 lines here is what wave dark matter predicts, depending on the mass we infer for the dark matter particle. All right. The dots here are the number density of galaxies that we've observed, okay, from the Hubble Space Telescope using the deepest images currently available for galaxy clusters and looking for lens images. So the points here are the the space density of galaxies at different magnifications in the cluster, okay, and you can see the data points here, all right, are different to our predictions for cold dark matter and conforms with what we expect for wave dark matter. Okay, so my graduate student is finishing up the paper, all right, and if we are correct, this would be the first strong evidence that dark matter in our universe is not what we've been thinking of for the last few decades. It is this much stranger form that's just been recognized over the past decade or so. All right, so let me wrap up with just a brief word about the future. Right, the future lies in 2 kinds of telescopes as far as observational cosmology goes. Okay, one is the James Webb Space Telescope. So this is the This is the next generation space telescope after Hubble. Okay, Hubble has been up there for over 20 years now. It's just about gone. All right. The James Webb Space Telescope is a factor of, is 3 times bigger in size. Okay, and it'll be launched in next year. Okay, and this is what a mock-up of it looks like. Right. This is the actual telescope itself. This is the shield which blocks the telescope from the sun. Okay, all right. At the same time, astronomers are building really big telescopes. The biggest telescope we have on Earth today is 10 meters in diameter. The next generation will be 30 meters in diameter, right? So we're building. Astronomers are building the. Oh, I forgot the 30-meter telescopes on Mauna Kea in Hawaii, okay, of which mainland China is a partner. All right? And the science goals of the next generation of big telescopes are all pretty much the same. Here are the main science drivers, which is what I told you at the beginning of the talk. All right. So the reason why my students and I are engaged in this work is really to prepare for the next generation. Okay, where we hope that we can solve, some of these outstanding questions in astronomy, as well as the nature of dark energy, which I haven't had time to talk about. Maybe next time. Okay, so let me stop here.